All right, my friends, this is very AP exam style. So for a problem like this, what I'd really hope for you is that you really do just kind of fall back on if in doubt, expand it out. It's probably the most empowering thing you could have in your back pocket when it comes to the series work that we'll have to do. So, and I know that I've expanded it above, but I'm just going to expand it enough until I can get out to a term that is, that would be 0.2. So anyway, so let's see, n equals 1, I'd have -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6, etc. Okay, so what is, so first of all, notice that this is a convergent alternating series. And then from there, if we're wanting the error or remainder to be no greater than 0.2, what that means is that we want the difference between this actual sum, which you could write it or you could just say S, and your partial sum. So I'm just going to leave a blank there. That is always less than the absolute value of your first neglected term, right? So how far out would we have to go if we're looking for your first neglected term to basically be 0.2? Well, 0.2 is 1/5. And so I hope it makes sense. We'd need to go out. We'd need this many terms. Whoops. We'd need that many terms right there for your first neglected term to be 0.2. So anyway, so it would be your fourth partial sum that you would need there. And then your first neglected term would be here, and that's 1/5. There we go. So the estimate that would be at least that correct would be this one. There we go. But I'm going to write it like this. I'm going to say the sum as n goes from 1 to infinity is approximately, whatever we had for that fourth partial sum. What did we have? Negative 0.583 repeating. There we go. Okay. And now a follow-up here. If somebody says, oh, well, what does that mean? One thing you could do is if we know that we are within 1/5 or within 0.2 of the real answer, you could actually add 0.2 and subtract 0.2 to this approximation. And so we could also actually say that we know the sum as n goes from 1 to infinity of -1 to the n of 1 over n in its true form is between negative 0.583 plus 0.2 and negative 0.583 minus 0.2. Like we know we're within 0.2 of that number for the real thing. So anyway, so that would mean the sum as n goes from 1 to infinity of -1 to the n times 1 over n is within, what would that be? Negative 0.383. It's below that number, and it's above this number. There we go. So that's kind of an interesting way where you can use your remainder to basically say, well, we know the actual answer is between these two numbers. And as you can see, like there's a ton, it's super inaccurate, but you could have used, maybe you could have used 20 terms, and then you would know your error is no worse than 1 over 21. There you go. Okay. Let's have you see if you can apply the same concept here. For example 5, you're supposed to find an approximation of the sum as n goes from 1 to infinity of -1 to the n over 1 over n squared that has an error no greater than 0.02. See how it goes.